Okay, so is my voice audible?
Yes, sir.
Okay, so let us continue with our discussions. In the last class, we discussed about image segmentation. Particularly, we were trying to understand how an isolated point can be detected and also how a line can be detected. Let us move on. Is the OneNote visible?
Yes.
Okay. So the next thing that we need to, in fact, study is about the detection of edges. So before we actually understand how I can detect an edge, we should understand what are the different edge models that we normally encounter in any image. Okay, and all of you know an edge is a point at which there is an abrupt change in the gray level value. So we have seen these type of examples in the last class. So an edge is a point at which the pixel value sudden increases or decreases drastically. So it can go from a dark to a brighter value or from a brighter value to a darker value. And when I'm using segmentation based on abrupt changes in intensity, I need to first detect edges. So let us just try to understand this with typical examples. Okay, so as I said, for example, if I have a variation something like this, 10, 10, 10, and suddenly the value changes to 100. So you see that there is an edge here. Okay, I'll just make this as 0. Sorry. So you see this is 10, 10, 100, 100. So you could encounter an edge here. There is a drastic change from gray level value 10, which is dark, to 100. Okay. So such changes, um, in fact, depending on how this change occurs, we classify edges into different models. So we will take one by one. For example, a step edge. In fact, what I have written already is an example for a step edge. Okay, so I'll write a 1D profile so that it is easy for me. So a variation something like this, 10, maybe 200 here. So what do you notice? Suddenly the pixel value is changing from 10 to 100. So this is an example for a step edge. And notice here, in this case, there is a sudden change from dark to white. Okay, so this is a place where it is changing. And in fact, this transition happens uh, over a distance of just 1 pixel. You observe here, this has happened over a distance of just 1 pixel. So this type of edges are called step edges. Now the second case is called a ramp edge. This also we have discussed. So we will take an example for a ramp edge, something like this, say 10, 10, 10. The value will not suddenly change to 200. It will change, first change probably to say 30, then maybe say 80, 100, maybe 200, etc. So you can see gradually it is going from 10 to 200. So the value will not change abruptly. It will change gradually. So it first goes to 10, then to 80, then to 100, then to 200. So that's what you see here. Such type of edges are ramp edges because the profile looks like a ramp. Then I think third one is self-explanatory. It is called a roof edge, which has intensity triangle profile like this. Okay, so what I mean is, um, it will be something like this: say 10, 10, then it goes to say 50, 100, 200, comes back to 100, 50, and maybe 10. So it has increased from 10 to 200 and decreased from 200 to 10. So that is what you see here. This is a roof edge. Okay, is this clear? The difference between a step edge, ramp edge, and roof edge, and along with examples. Any doubt?
No,
Any
sir.
doubt?
Clear.
Okay. So let us take an example here. This is an example of a medical image. Actually, it is an example of a head CT image. Uh, I think the zoomed portions are actually telling you what type of edges you are having there. For example, if you just look at this, of course, it is not a very straight, okay, ramp like this, but you can see it's almost like a ramp. So there is a ramp edge here, and you can see sudden transition here. So you can say this is a step type of step edge, and you can see a triangular type of edge in this corner. So this picture is actually is an example of a head CT image which demonstrates all the three edges that are possible. Okay. Now, whenever I want to detect such type of ramp edges, we need to understand how these first and second order derivatives can help us. In fact, we have already discussed this in detail in the previous unit 2 also, but let us just continue discussing it because this is a very important component. Now, a first derivative, observe an example here. What is taken is the first few okay, pixels are dark. So that is why you see, I hope you can see the profile. Let me just zoom it. Okay. So this is dark. Then from darkness, it is gradually increasing to bright and then it is constant bright. So the profile is like this dark, then it has a ramp edge and then it becomes a constant. Now, if I use derivatives on this, all of you know, first derivative will give me like this because derivative of a constant is 0. So this is already 0. So derivative of that is 0. Again here derivative of a constant is 0. Now derivative of a ramp, we know it is something like your the equation looks like y is equal to at. So if I differentiate it with respect to t, dy by dt will be equal to a, which is a constant. So that's exactly what you see here. Okay, so this is derivative of a constant. Then suppose if I further differentiate this, definitely you know differentiation of a constant is 0. Therefore, in this portion it is 0. Okay, differentiation of a constant is 0. And whenever you have a step edge like this, that means a sudden rise or a step like this, you know second derivative will pass as it is to the output. Okay, so therefore I'll get a spike here, a positive spike going from 0 to maximum. Now there is a negative transition from positive value to 0, so you will get a negative step here. So this is actually a positive spike, this is a negative spike. Suppose if I join this okay tip to this tip by a straight line, the point where it crosses the x-axis, we call it as a zero crossing. Okay, so this is the output of a second derivative. Now let us just try to understand uh, each one of them and also compare it with the results. So what you notice is first derivative at the onset of the ramp. The onset means the point at which it is starting. At that point, it is positive. So observe it here. The ramp is starting. so it is positive. And on the ramp, that means in this region of the ramp, it is constant. On the ramp, okay, it is positive. You can observe. So it is positive here and positive here. And in the constant region, in this region, it is 0. Okay, so I don't think there is any difficulty in following it up. Okay, now when it comes to second derivative, at the onset of the ramp or the beginning of the ramp, it is positive. Observe here. And at the end of the ramp, it is negative. See, the ramp is ending here. You can see that it is negative here. Okay, and along the ramp, the value is 0. You can observe. Along the ramp, the value is 0. So that is the observation. Okay, now the intersection between the zero intensity axis and the line between extrema is called zero crossing. That's what I told. Okay, this is the intensity. Okay, zero intensity axis, and these are the extrema points of the second derivative. So when I join them, what I get here is a zero crossing. So this will actually locate the midpoint of your ramp actually. Okay, so the ramp midpoint. So you will know which is the midpoint of your actually roof edge here. Sorry, uh, ramp edge here. Now magnitude of first derivative detects presence of an edge. So if I just take magnitude of this, obviously you'll get a positive value here. So it will tell me that there is an edge in this point. Sign of the second derivative detects whether an edge pixel lies on dark or light side of edge. For example, see here it is going positive. So I can say this is a dark pixel. Here it is going negative. So I can say this is a lighter pixel. This is a darker pixel. This is a lighter pixel. So that's what it says. And as I said, zero crossing locates the center of the thick edge. So when an edge is like this zero crossing exactly tells me the center of the thick edges. So what you can do is whenever you are detecting edges, if the thickness of the edges is very large, just to reduce the thickness of the edges, I can use this zero crossing and make sure that I will reduce. That means we call this as edge thinning or thinning operation, which we will discuss in the next unit. So zero crossing will help. Any doubt so far? It is self-explanatory, but still if there is any clarification, let me know. Any doubt? Please respond.
No, sir, no doubt.
Okay. Now let us try to understand the behavior of these two derivatives whenever there is a noise in the image. See, noise is not in our hand. We can expect the noise to affect the pixel values. So obviously, different derivatives, they are sensitive. Particularly, you have seen that second derivative is very sensitive to noise. So let us try to understand that. Now, what you see here is, I think the legend has to be read first to understand it. So this is, just read this. So the first column are the images and intensity profiles of a ramp edge corrupted by random Gaussian noise of 0 mean and standard deviation of 0, 0.1, 1 and 10. That means here the noise standard deviation is 0. In this case, the noise standard deviation is 0.1. In the next case, the noise standard deviation is 1. And in the next case, the noise standard deviation is 10. Okay, that means sigma is the standard deviation of the noise. So the noise is assumed to be Gaussian. You have seen in the previous unit, that is image restoration, how noise can be approximated as a Gaussian noise with variance and mean. And in this case, mean is considered to be 0 and standard deviation is varying. As you notice, when I go from top to bottom, you can observe that the noise is increasing in the image. Okay, so this is the example. Now what you see here is the first derivative. Okay, this is the image, this is the image, This is the image, and this is the first derivative. The second column is the second derivative. Okay, so now try to understand. If I come here, this is the original image with zero noise. This is the original image with zero noise. So it is a ramp edge, as you can see. And if I take the first differential derivative, what you see is wherever it is constant, the differential of a constant is 0. So you could see that 0 here. That is why this region is dark. This region and this region is dark. And whenever there is a ramp, see there is a ramp here, differential of a ramp, just now we saw it is a constant. So you could see that constant here. That constant is seen here, and that constant gray level is shown here. Okay, this is first derivative. If I do a second derivative, you know that you will actually get a spike in the onset of the ramp, a negative spike in the at the point where the ramp is ending, whereas near this region it is dark. The reason why it is dark, differential of a constant is 0. I think there is no problem in this because this is same as what you have seen here. Both of them are same. But the question is when the image is corrupted with noise. That means when the image is noisy and the noise is not too much, as you can see, it is 0.1. Now observe, this is the ramp. There is some variation along the ramp, but that is very less because the noise is less. So when I differentiate it, as you know, differentiator is sensitive to noise because differentiation is going to give you what is the change. So differentiation, I think all of you know, it gives me the change in the values. So you can observe that there is some noise here, there is some noise here, there is some noise here. But still, I can say there is an edge because this magnitude is much higher, as you can see. So I can say there is an edge here. But look at the second derivative. What do you notice? Can I say that there is an edge here? Here I can say because I could see a positive spike and negative spike. Here I have to be very carefully watching this and say there is actually an edge here. These two spikes will correspond to that. Okay. Now, can somebody explain what has happened here? What do you okay conclude from this next image? This image. Let me just take some name only. If you Rahul Kumar.
Yes, sir.
Yeah.
Sir,
Okay. Can you?
in this graph, we can see there is a noise in the ramp also as well. And after the first derivative, we saw the noise, a lot of noise is there in the first derivative. So it is very hard to differentiate, but we can differentiate in the first derivative.
Correct.
But as we
Yes.
move on to the second derivative, there is very less chance means we can't able to differentiate where we got the positive edge as well as negative edge.
Very good. Correct. So to some extent, first order derivative can tell me that there is an edge here because you could see the constant region here and you can separate them. But here it is very difficult to locate these 2 points. You cannot say because the other noisy spikes are much higher than these two. So I cannot do any segmentation here. And in fact, the last case is the very bad case wherein even first derivative also cannot help me, as you can see. Okay, good. So what we notice is as the noise increases, to some extent first order derivative can still help me, but second order derivative starts failing. And when the noise is very high, none of them can help me to detect the edges. So something has to be done to take care of this noise prior to segmentation. So whatever we discussed in third chapter or third unit, that is image restoration, some noise filtering phenomena has to be used prior to going for edge detection. Okay, I hope you understood now. So the observations, I think all of them I have explained, but still let us read them. So for noise-free case, first derivative of a constant is 0 and of ramp is a constant. I think this is well understood. As the noise increases, the first derivative becomes different. It is difficult to associate the derivative to the rampant, particularly for more noise. That's what you have seen. For less noise, to some extent, I can associate. For more noise, I cannot do that. Second derivative is even more sensitive to noise. That's what we have understood. For noise free case, second derivative gives a thin white line. I think you should have observed that also. Let me just zoom it. I think this is the maximum scale. So do you see a white line here and a black line here?
Yes.
Yeah. So this corresponds to these spikes. A white line here and a black line here. That's what he says. Second derivative gives a thin white line at the onset of the ramp and thin black line at the end of the ramp. Okay. Now second derivative of constant, actually it is 0, all of you know, but notice here it is shown as a gray shade. So don't think that this is true. Actually, to show this result, they have scaled everything. That is why this is looking to be, because observe here, in the ramp region, second derivative has to be 0. So if it has to be 0 means this should have been looking dark, just like what you see here. But to show these values, that means to show these thin edges here, to demonstrate, this particular image is actually scaled. That's what he says here. Second derivative of constant is in gray due to scaling. So some scaling, that means you have just increased all the gray level values so that you can see all of them. So don't think it will be gray, it will be 0. I hope you understood. Okay. Any doubt so far? Sorry. Any doubt? Can I move on?
No doubt, sir.
Okay. So now let us see how we can detect edges. Just now we understood that noise is going to affect the segmentation. So it's better to remove that noise. So the first fundamental step that we follow in edge detection is first reduce the noise. For this you can use any type of filter that you have already studied in the previous unit, that is image restoration. So apply smoothing first so that the noise is removed. Okay, then you need to detect the edge points, because you need to find the edges. So what is an edge point? All of you know, edge point is a point at which the gray level value has drastically changed. It would have changed from very low to very high value, or very high to very low value. So I need to detect these edge points, and I think we know the Laplacian can help us in detecting these edge points. So I need to find all these edge points, and I should say these are the potential candidates of edge points. That means they will be lying on the edge. Then localize them, because some of them may not be edge points, because of some variation you would have got them. So you need to localize them. That means you need to select a candidate edge point which are actually the true members. Okay, which are having edge. So that could be done by just referring or comparing it with the neighboring pixel values. Okay, so let me repeat. First step is smoothing, second step is detection of edge points, and third step is edge localization. So in the previous unit, that is unit 2, we discussed about gradient operators also. So we are revisiting it again. Either I can use first and second order derivative to detect the changes in intensity, okay, which will help us in edge detection, or you can further simplify. I think, let me just, so for example, one of the kernel that we used is a Laplacian. This is one of the kernel. So I need to apply this onto the image. So whenever I need to do, I need to multiply it with this -4 and add to these values, and you have to calculate the resulting value. If I use some approximations, I can avoid multiplying with constant also. I can just have only values like zeros and ones. So let us try to understand that. Now image gradient, it actually finds edge strength and direction at any location. I think all of you know what do you mean by a gradient. A gradient means I need to take a partial derivative along that particular direction. So if a gradient along x direction means I have to take partial derivative along x direction, and I take partial derivative along y direction, and then the magnitude of the gradient can be determined by just taking square on the derivative and root of that. So gradient along x direction squared, gradient along y direction squared, and root. And this can be approximated. This can be approximated by just using gx and gy. This is what we discussed in the previous unit. So of course, if you want the direction of the gradient, then I need to take tan inverse of gy by gx. So now what we do is to apply this gradient operator. That means we will not do this gradient along x plus gradient along y and then root. What we actually do is we'll just approximate this. We'll just approximate this as g of x plus g of y. Now what is this g of x? Yeah, I just do this operation. Something like f of x plus 1 minus f of x. Just find the difference between the two pixels. Similarly, f of course, I'm sorry, I need to consider y operator also. So this will be f of x plus 1 comma y minus f of x comma y. So this will give me the gradient along x direction. To find gradient along y direction, I'll do this f of x y plus 1 minus f of xy. So as you can observe, you are just subtracting the pixel value from the neighboring pixel value. Okay, so you don't have this constant like 4 or anything. This is, in fact, the coefficient here is plus 1, the coefficient here is minus 1. So you are to just either add or subtract. Addition or subtraction doesn't take in fact much time on computer, so we use such type of kernels. For example, observe here, in this case, this value is 1, this is 1, and this is minus 1. So can somebody tell me what type of edges it will detect? What type of edges this type of kernel will detect? We have already discussed this in unit 2. The repetition. Diagonal edges. What is there? So an edge in this line. Okay, so it's a diagonal edge. This is also for a diagonal edge. So any change along the diagonal direction it will detect. Okay. So such type of operators are called Robert operators. Please remember this. These two are Robert operators. Now to find horizontal edges or vertical edges, Previtt has suggested other kernels which are here. Okay. Again here, this can detect a horizontal line, and this can detect a vertical line. All of you know that. Now Sobel has slightly modified them. He has given more weightage to the center pixel, as you can see here, and less weightage to the other pixels. So the advantage of this is the edge exactly the edge pixel is given more weightage. Okay, more weightage to center pixel. So that means the edge pixel is given more weightage. That is the advantage. Okay. Now Sobel has also suggested filters which can help you in detecting diagonal edges. Observe here, these values are positive and these values are negative. In all the cases, what you should notice is if you add the weights, it should give me 0. Okay, please notice that if you add all these weights in the within a kernel, it should give me 0. So this and this, they are helping you in detecting diagonal edges. This is actually the Previt uh, uh, kernels which can help me to detect diagonal edges. Okay, so what you should notice is, of course, except Sobel, Roberts, Previt, the entries are +1 and -1. So there is no multiplication at all. You are just performing negation operation. So that way computationally they are fast, and they are approximate filters which can give me the gradients or which can detect the edges. Have you understood this? Is this clear? Is this clear? Any doubt? Nobody want to comment? Am I audible? Am I audible?
Yes, sir.
Okay. So any doubt?
Yes, sir,
Anybody?
you are audible.
Okay, okay. So I'll assume that because they are all simple operators, what you should notice is instead of using a kernel like this where you have to multiply the center pixel by -4, which will be a multiplication which needs some computation, we have made an approximation and we have now these filters. These are called as the gradient operators suggested by Roberts, Prewitt and Sobel. Okay. Uh, These gradient operators will help you to detect edges along different directions. I will only explain one of them, but you should try for all because these type of problems will be given. Let me just take an edge. I will just take an edge. Assume that I have an image of this nature. Okay. Of course, I have taken a very small image, 3 cross 3. It can be a bigger size image, but just to start with. Now, if I have to detect this type of edge, which filter I should use here? Can you tell me? Which of them will help me to do this? Which one I should use? Observe the image and also observe the kernels. Anybody? Nobody want to comment?
Sobel
Sobel, yeah, Sobel can be used. Yes,
or
yes, Sobel can be used. Which one?
Pervit
Which one? Sobel, which one? For example,
down.
I'll call this as A, I'll call this as B. Actually, they are labeled here. So, should I use A or B?
A,
A, correct. Okay.
A.
So, if I use a Sobel filter of this nature, -1, -2, -1, 0, 0, 0, 1, 2, 1. Okay. So, when I apply this on this, what will be the center pixel value? Other pixels you cannot calculate exactly because the neighbors are not known. I just want the center pixel value, this value. That means this filter has to be applied on it. So in fact the center values, all of them are multiplied with 0. So it is something like -10, -24, -13, +15, +26, +14. What is the value you get? 10 into -1. I hope you are understanding what I am trying to do. 12 into -2, 13 into -1, plus 0 into 200, 0 into 200. See, these type of problems can be given in exams or tests. So please learn how to do it. 15 into 1 plus 13 into 2 plus 14 into 1. What will be this value? Quick. Whatever value you get, you have to replace this center pixel. Okay. Have you understood how to calculate it?
Yes, sir.
Yeah. So in tests or exams, what normally is done is an image like this, probably it would be a bigger image will be given because a smaller image like this, you cannot calculate the other pixels. See, these pixels, if you want to calculate, no, you need the corresponding neighbors. But I don't have these neighbors. So what they do is they will actually give you a bigger image. The only thing is the border pixels. Okay, you can neglect them. You can just need not worry about the border. Okay, these border pixels, but the rest of the pixels you have to calculate. All these pixels you have to calculate. Okay, and you have to give the uh, resulting value. So do you think you can do this? Because for want of time I may not ask you to solve it now. So please take some bigger image like this. I think MATLAB can be used, but manually you will be asked to calculate. Or the other way of asking is demonstrate the use of Prewitt filter or Sobel filter for detection of different types of edges with an typical example. So you must know what typical example you have to take. Okay. So with this, I think let us stop. It's getting late for me. So in the next class, we will probably continue with how these type of filters can be used and how we can do segmentation by using region-based segmentation.